Hi, my name is Maddie Matthews, and this is my Physics 2212 Lab Report 3 on circuits. So, a quick introduction before we start. The purpose of this lab was to predict the behavior of circuits containing resistors in series and parallel. And we did this by using multimeters to measure the actual values of conventional current and potential differences in circuits and examining the behavior of ohmic resistors and capacitors. And we did this using physical circuit equipment in lab and then Excel to graph our results. And a quick overview of our results are we had two different circuits that we examined. So for the simple circuit, we found that the overall voltage was 0 volts, and then for the RC circuit, time measured was around half of the expected value, and we found that increasing resistance changes or increases charging and discharging time. And some fundamental physics concepts at play here. First is the node rule, which relates to charge conservation, and it says that current flowing into a node must be equal to current flowing out of it, or IN equals I out to simplify it. And there's a little picture in the bottom left corner. And then the loop rule relates to energy conservation, and it says that the sum of all electric potential differences in a loop is 0, and then the picture is in the middle, and then Ohm's law is V equals IR, and it says that the current through a conductor between 2 points is directly proportional to voltage across the points. So here's the setup for our first experiment, which was the simple circuit. We had that the system was the circuit, which was two 1.5V batteries, 2 resistors, and 2 ammeters, and the surroundings was everything else. And then we did a quick little calculation of the V equals IR, as you can see here. And then here's what the setup looked like, and then a picture of our actual circuit. And from there, we were able to calculate electric potential and then sum all of those up. And you can see on the right is the actual graph of electric potential versus position throughout the circuit. And we found that the actual expected value was 0 volts, and that's what we got when we did the experiment as well, by summing up all of these numbers over here, so you can see that they sum up to 0. And then some calculations to find, for the 47 omega resistor, we found that it was 47.5 omega, and then for the 100 omega resistor, we found 102.5 omega, and then for the wires and ammeters, we got 0. And then here is our second experiment, the RC circuit. So the system was the circuit that was two 1.5V batteries, one IF capacitor, and then a few light bulbs, and the surroundings was everything else. And what we did here was we connected each light bulb to the battery circuit and measured charging and discharging periods for each of the light bulbs. And here's a picture of the setup again, and then our actual circuit in lab. And for light bulb 1, which is 10 omega, we found the charging period to be 15 seconds and discharging period to be 16 seconds, which you can see on the graph over here. And then for light bulb 2, 20 omega, we found the charging period to be 29 seconds and discharging period to be 32 seconds. So what we can conclude from this is greater resistance equals less current flow. So the capacitor will take longer to fully charge or discharge with greater resistance. Some possible sources of error in this lab are just human error from visual observation of the light bulbs. So it was kind of hard to measure the exact moment on the stopwatch, like when the light bulb would turn on and turn off. So we could take more measurements or samples to minimize this error, since we didn't have that many samples of the light bulbs in our calculations. And then discussion question would be, what if you charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? How would this prediction happen in real life? And then use an ammeter to measure how long it takes to charge the capacitor when connected directly to the battery, and then discuss why the measured time is different from the predicted time. So voltage law here predicts that the capacitor would charge instantly in a theoretical situation if there was no resistor in the circuit, but this does not happen in reality. So when we used an ammeter to measure exactly how long it took to charge the capacitor connected directly to the battery, in real life it took about 5 seconds, and that's because wires themselves have internal resistance, and there's just resistance in the whole circuit. So the measured time is going to be different from the predicted time, even though it predicts that this should happen instantaneously. So thank you for listening.